let's look at the Galerkin formulation. Okay, so we're going to be looking at the Galerkin formulation. If you recall, first we stated the strong form of the problem. We say, well, now my differential equation has to be satisfied everywhere along the bar. But we said, well, maybe that is too strict a requirement, and so we're going to relax that, and we're going to say, well, how about we just simply satisfy equilibrium on average? And then we go to the variational form of equilibrium. Remember, again, that those two are actually, in a way, equivalent because of what? We said it multiple times. We are living in a infinite dimensional space. Essentially, we can come up with any function. And if I can come up with any function, I can obtain the exact solution. Now, obviously, this is really not practical, right? We don't have resources to deal with infinite dimensional spaces. I cannot put that equation in a computer, right? Well, I could, but for the most interesting problems where we have to come up with some sort of mechanical part, for instance, I cannot really deal with that problem. I don't have infinite resources. I cannot crunch infinite numbers in a computer. So we have to relax that requirement as well. And now the idea is that we're going to try to project into a finite dimensional space, right? And so we have n number of variables to solve, and then I can start doing some number crunching in a computer, and I can get my result. So now the objective is to go from infinite dimensional spaces to finite dimensional spaces so that we can actually work with them, right? And so that is the whole point of the Galerkin projection. We're going to look at the orthogonality of the Galerkin error, and then there is a proof and computation of the error. These are the things that we're going to look at today. And by the end of today's lecture, this is going to set the basis on which we can start doing some finite element simulations, and then we can compute some strain energies. And because we can compute the strain energies, we can compare them to the so-called exact value of the strain energy. And if I have an exact value, I can compute what? Errors. I can compute errors. And if I can compute errors, I can plot that error, right, in the energy norm as a function of, let's say, the mesh size. And I can have some understanding of how that error is going to be reduced as I decrease the element size. And this is convergence analysis, right? And we're going to see how that error goes to zero as I reduce the mesh size or as I increase the polynomial order, right? And there are some theoretical values on those convergence rates, right? And so some are optimal, some are going to become suboptimal. And so this is what we're going to learn in this course. We're going to learn that there are some problems that are simple to solve, and there are some problems that are more challenging, for which the convergence rates are going to be a bit lower, right? Okay, so let's get started. Again, we are dealing with infinite dimensional spaces, so you could argue, well, how does a function look like when you are dealing with infinite dimensions? Well, you could write it something like this: u of x is the sum of phi I ui I equals 1 to infinity, right? Phi I is essentially a basis that spans that energy space, and ui is the so-called degree of freedom, right? So those are just coefficients that are scaling each of the basis functions. You all have seen that in the past. But now, again, because what we want is to have to deal with finite dimensional spaces, what we're going to do is I'm going to define a space EH, and you notice that I say explicitly that it's going to be a subset of the infinite dimensional space. And so the Galerkin form, if I want to just simply state it in abstract form, is simply find UH that belongs to that finite dimensional space EH, such that, again, the bilinear form equals the linear form for all test functions in that finite dimensional energy space. So this is the equivalent. So I take essentially my well-known bilinear form, linear forms that we got from the previous lecture, and now I'm just dealing with functions UH and WH. And again, if you recall this from nonlinear mechanics class, we use the symbol H to denote the mesh size, right? H is a symbol that we normally use to denote the mesh size, and so whenever you see a U superscript H or a W superscript H, you know already that we're dealing with finite dimensional spaces, right? And because we're now dealing with a finite dimensional space, I don't get the exact solution unless for a few simple types of problems for which, it just happens that you can obtain the exact solution. In one dimension, it's very straightforward, right? You take the differential equation, you integrate twice, regardless of let's say the force per unit length, and then you get two constants. You can obtain the constants of integration by applying boundary conditions, and then you get the exact solution. So in 1D, it's actually very straightforward. But in 2 dimensions and 3 dimensions, unless the problem geometry is very simple and the loading is very simple, and you exploit some symmetries and so on, getting the exact solution becomes nearly impossible. And so the Galerkin projection is our tool to get a solution as opposed to get no solution, all right? But we accept that there is going to be an error. So is that good or bad that we have an error? Why is good?
You can approximate the real solution, but you can actually calculate it more simply, so you can do it a lot of times.
Yeah, so you can approximate the exact solution. I mean, we know that this exact solution should look like somehow like the approximate solution that we obtain. And well, how good that solution is, right? Is that a good solution or a bad solution? Well, we don't know. So we need to build the knowledge to understand whether that error is appropriate. We are engineers, right? Yeah, it's okay. I can live with this error as long as you know how much error you're having. Yeah.
Did you start recording?
Yes, I started. So as long as we can understand the error and we can control it, remember we talk about convergence rates, right? And so if I know that if I reduce the mesh size by half, I know more or less how much error is going to be reduced, because theoretically I have some convergence rate, and that convergence rate applies to this type of smooth problems, then I have a much better understanding. Now, you may argue, well, for most problems, you don't have the exact solution. So how can you compute errors? Right? Who has an answer to that? Yeah?
Look into the change of the solution when reducing mesh size.
Sorry?
So if you reduce mesh size, there is a change in the trial solution. Maybe you can reduce.
Yeah, when you reduce the mesh size, there is a change in the solution, and so your solution gets more appropriate. You're going in the right direction. Well, as it turns out, we can actually approximate the exact strain energy. How is that? I mean, you are using a finite dimensional formulation to get an approximate solution, right? How is it possible that you can approximate the exact strain energy? Well, as we will see later in the course, there is something called a posteriori error estimation, where you simply solve the finite element problem 3 times, and with these 3 values of your approximate strain energy for, say, different mesh sizes, you can actually get an approximate value of the exact strain energy. Now that I have an approximate value of the exact strain energy, now I can compare the results and I can understand how good or bad the error is. You have a question?
Yeah, just to clarify, when we talk about the strain energy, are we talking about strain like in the mechanics sense, or?
Yeah, totally. It's mechanical strain we're talking about.
So this doesn't apply for other problems where you use finite element but you don't have a strain energy?
Well, it applies to all the problems. Of course, when we talk about all the problems, it would be nice to define what those problems are. Everything that we're looking in this course is can be applied to elliptic problems, elliptic differential equations. The method of finite elements is also good for parabolic problems, right? For hyperbolic problems, things get a little bit more complicated, so there are better tools for that. So there is better hammer for that nail, right? But yeah, we don't, when we talk about heat conduction, we don't talk about strain energy, right? But we talk about heat energy, right? So there are equivalent in other problems as well. All right. Okay, so let's look at the Galerkin projection, because now what we're going to do is we're going to take UH and WH, and I'm going to take them from the same space, right? As long as they are chosen from the same space, if you recall, this leads to nice properties, right? My bilinear form is going to be symmetric. If you recall also, the bilinear form is going to lead to the so-called stiffness matrix. The fact that my bilinear form is symmetric means that my stiffness matrix is going to become symmetric, which is great because now I require less storage, less number of operations. With a direct solver like Cholesky factorization, I can get the solution faster in a way, right? That doesn't have to be the case, and there are problems for which a Petrov-Galerkin formulation is more suitable. In a Petrov-Galerkin formulation, you take the trial solution, UH, which is no longer the exact solution. I'm going to be calling it from now the trial solution because, again, remember that I am accepting that there is going to be an error, right? So I call it the trial solution. And then I'm going to take my test functions from a different space. If I do that, now I lose symmetry. My stiffness matrix is no longer symmetric. And then you may argue, well, why do you choose from different spaces? Well, there are problems for which you need to do this, otherwise you don't get a good solution, right? And I always quote, for instance, the SUPG formulation, the streamlined upwent Petrov-Galerkin formulation, which is the way to solve for fluids in finite elements. Before SUPG was proposed, then you could not really solve for convective problems because you had oscillations in the solution, and so someone had the idea, well, let's just pick these functions from different spaces, and then let's see whether you can actually incorporate some information about the problem that you know, so in this case, convective terms, and then you were able to obtain the solution using finite elements. That's why I guess finite elements were not really the most popular choice when it comes to fluids, but people choose for finite volumes. But again, just to finalize, the idea is that you can either choose this trial solution and the test function from the same space or from different spaces, and they are going to be called either the Bubnov-Galerkin or the Petrov-Galerkin form. Let's talk a little bit about the error. So, and this is remarkable. So we can write our statement of again equilibrium in average sense like this, right? The idea is find U such that the bilinear form is equal to the linear form for all functions W. I'm in infinite dimensional space. Notice that there is no H here. Now I'm going to write this second equation where I basically choose only test functions that are in that EH subset, right? So this equation, of course, is valid because this EH is a subspace of E, so of course I can write it that way. And now I'm going to write the Galerkin projection for which I have these two functions UH and WH. So I'm going to take these last two equations and I'm going to subtract them. The moment I do that, I get basically that the left-hand side can be written B of U minus UH, comma WH, and of course the right-hand side is the same. And what you see in this expression is that the bilinear form, right, applied to the U minus UH, which is what? What is U minus UH?
Error.
This is the error, right? I have the finite epsilon here. That's my error. So the bilinear form of the error is equal to 0 for all test functions in that subset of the infinite dimensional energy space that I call EH. And this has many, many, many interpretations. And we're going to talk a little bit about that. So you could see that in a way, this relationship here is saying that U minus UH is orthogonal to the entire subspace EH, right? Of course, we're talking about these things in the sense of the bilinear form, right? Again, the error is orthogonal to an entire space, and it's very hard to visualize that. So in a minute, we're going to get into like a more easy way to visualize this with Euclidean spaces that I find always useful. But think about it this way. Somehow I'm saying that the error, right, is not orthogonal to a function. is orthogonal to an entire space of functions, right? And that essentially means that it means two things. It means that UH, which is the solution that you obtain, right, the trial solution, is essentially the projection of the exact solution onto the space. Right? It's like you're projecting the exact solution into that space. And it also means that from all those functions that you have in that subspace, somehow you are picking the best possible solution, right? And this is the crazy part. You were dealing with a projection where you're looking at an infinite number of functions. Remember, even if I'm dealing with a finite dimensional space, let's say I have 10 coefficients, right? Well, those coefficients are real numbers, so I have essentially an infinite number of them, right? So from that infinite number of functions, the Galerkin projection is picking up the one that minimizes the error with respect to the exact solution. And that is the crazy thing. And that is what I really think that this is an incredible invention, right? So the finite element method as we know it today would not be possible without the invention of the Galerkin projection. And of course, claiming that the Americans were responsible for the invention of the finite element method in the 50s, right, in their NASA program, yeah, that is very limited because we have to really give credit, and the credit goes all the way back to Bubnov, to Galerkin, Timoshenko, all these guys who were really talking about these methods, Rayleigh-Ritz method. Who know about the Rayleigh-Ritz method? Yeah. So there was a progression over time that, in a way, was using this incredible result. The fact that I just plug functions, right, and I know that the result that I get is the one that minimizes the error with respect to the exact solution is crazy, right? And of course, it's the basis for what we do in finite element simulations today. So let's visualize that, right? And of course, I like visualizing this with Euclidean spaces because we all have already these ideas of what happens when you're dealing with Euclidean spaces. So if I have my exact solution, this is U, right? Well, remember that UH is the projection of that into some space. So in this case, U is a three-dimensional vector, but let's say that I have a subspace that is two-dimensional. Well, if I take that U minus UH is that vector, so that is essentially my error. So the Galerkin projection is actually projecting that three-dimensional vector like this. So my error is orthogonal to that space, right? Now, this is Euclidean spaces, so we all understand what this means. What we did in the previous slide, we're dealing with functional spaces. So trying to, marry these two ideas is hard, right? We're dealing with somehow abstract concepts, but the ideas are the same. Remember that as much as we have Euclidean spaces and we can measure things in Euclidean spaces using norms, well, we also did the same with functional spaces. Now we have ways to measure functions, right? Yeah?
What are the dimensions of those spaces here, just for illustration?
No, of course, this is just for illustration because we cannot visualize anything beyond 3 dimensions, right? But now we're dealing with functional spaces. So think about a finite element simulation where you have 1 million nodes, right? And now it's a 3-dimensional simulation, so every node, every finite element node has 3 degrees of freedom. So now you have 3 million degrees of freedom, right? As opposed to infinite. But that is the idea, right? The idea is that now the Galerkin projection is a means to obtain a solution that somehow minimizes the error with respect to the exact solution. So that is why in the beginning of the, when we were talking about the Galerkin, the variational form, remember I told you that method we use is called the method of weighted residuals, right? Because we're taking a weight function and then we're multiplying by the differential equation that eventually when we are in a finite dimensional form, that differential equation is not going to be equal to 0, right? It's not satisfying everywhere point-wise. It's going to be some residual, and therefore the name method of weighted residuals. Okay? Okay, so there are a couple of, let's say, proofs that I wanted to go through. Of course, everything that we have tried to see in the previous slides, is very difficult to visualize, but we can prove it mathematically. So the fact that UH minimizes the error with respect to the exact solution mathematically means that from all functions VH in that subset of subspace, right, UH is actually the one that minimizes, so that's why I said argmin, right, of U minus VH in measured, of course, in the energy norm. Okay, so there is this proof. There is really no need to go in detail through it, but we do a proof by contradiction. So let's assume that there is some function VH that has a lower error, right? So then when you plug these things into the error square, you can write it. Of course, the error now is going to be U minus VH, right? That's going to have a higher error. And then when you do the proof, you basically add 0 here, you get rid of some terms. But then in the end of this proof, you get 0 is greater than something that looks like this. And we know that there is a property of the bilinear form, if you remember, that is greater than or equal to 0 when applied to the same function. That was one of the main properties of the bilinear form. And so this cannot be true. Therefore, we can say that UH is actually the one that satisfies or minimizes the error with respect to the exact solution. And you can see that in more detail later at your own pace. There is also another mathematical, let's say, statement that I want to discuss a little bit, because this is the one that we're going to be using to obtain errors when we obtain our approximate solutions using finite elements. So essentially, if I want to measure the error with respect to the exact solution, this is essentially going to be the same as simply taking the square root of 1/2 and then I subtract the bilinear forms of the exact solution and the approximate solution. And this is very good because, yeah, you could argue that in finite element analysis there are two ways to compute errors. If you have the exact solution, right, I can try to compute the error by integrating U minus UH, right? In the sense of the bilinear form, again, we're always talking about the bilinear form. And because I'm talking about the bilinear forms, I'm not integrating the functions themselves, but I'm integrating the derivatives. Remember that in my bilinear form that leads to a stiffness matrix, I have derivatives, okay? And so if I have the exact solution everywhere in my domain, I can go element by element at each Gauss point, and I can evaluate U minus UH, which is my error, and integrate that, again, in the sense of the bilinear form, and compute some value of the error for the entire solution, right? I can aggregate that integral for each element, and I'm going to get a value, and that is going to be my error. But it is way more simpler than that, right? So what this proof tells you here is that you just need to compute the approximate solution, then you compute the strain energy of the approximate solution, right? You compute the strain energy, and then you can simply compute the error by subtracting that strain energy with the exact strain energy. And I say strain energy and not bilinear form because if you notice at the end of the result, simply because there is this relationship between the bilinear form and the strain energy, I can simply compute the error by just taking the difference between the strain energy of the approximate solution and the exact solution. I take the difference between those two, right? And this is the proof that is telling you that. And again, you can go through the proof at your own pace. It's not really important that we do it here. All you have to note at this point is that now there is a way for us to compute errors, right? Okay. This is a shorter lecture than the previous one. Now we are ready to delve into finite elements. We are ready to start plugging in equations for the test functions that we're going to use. And then we are ready to compute an approximate solution. We are ready to compute an error with respect to the exact solution. And we are ready to compute convergence rates. And so what we're going to start doing soon, and this is, again, something that I want to do with all of you, we're going to go through the project together and finalizing the project. And so I should be able to have the project either today or tomorrow in the Brightspace. And once we have that, we're going to start working at the project all together. Meaning, we're going to look at the code, and we're going to start crunching some numbers. We're going to have everybody setting up their Python environment system so that we can run the code. So we're going to try to do this together, okay? Any questions related to the Galerkin projection? It's clear?
I need to work on it, but
Yeah, it's going to take a bit of time to get used to these ideas. Again, it's not going to get more difficult than today's class. So the most, I guess the most abstract idea that we're going to see is this idea of Sobolev space, what it means. That's it. Other than that, everything else is very, very straightforward. Yeah?
Yeah, in the previous slide, when we do error, we get functions that were in two different spaces. We're in the finite space, and we're also in the infinite space.
Yeah.
But how does that work exactly? Like, is it just something you can do?
Well, think about it this way. If you were working in an infinite dimensional space, you're also working with a subset of that space. And of course, that subset of the space includes your VH and your UH. Yeah? Yeah?
How do we calculate the error if we don't know the exact solution?
Yeah, we talked briefly about it. That's what we do in this class. So as we said, there is a way to approximate the exact strain energy. So when we look at convergence, of these methods, we get into something that is called a priori error estimates. So in a way, we understand how the error is going to be reduced because the theory tells us that error is going to be reduced in a certain manner, right? Okay, well, if now I have this equation from theory that is telling me that the error should reduce in a certain way, right? And then I solve three different problems, I can use the result of three different solutions to get or extrapolate what the exact strain energy would be. And that is going to be, again, part of a project. So you are actually going to be able to do this yourself. And you're going to see that the strain energy that you obtain by using this procedure is actually very, 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 very close to the exact strain energy, within 1% of its value. Which is crazy, right? Because indeed, you don't have an exact solution, but now you have a means to approximate its exact value. Yeah?
Well, what's the error between the approximation of the exact error and of the exact solution and the exact solution itself? Because it could be 1% off of the approximate, but if
Yeah.
the approximate solution is 10% off.
No. What I meant is that for the project, you will see that it's 1% with respect to the exact solution, which is really, really crazy. And of course, you could say, well, this doesn't really make a lot of sense, right? This guy is saying that three solutions, they are approximate, and then I can obtain an approximate value of the exact strain energy. Yeah, but if that is the case, do any three finite element solutions lead to the same value? Yeah, obviously not, right? So say you take three finite element solutions, and then you get an approximate value. Can that approximate value get more approximated to this exact solution? Yes. Now, if I take, instead of those three more refined meshes, I'm going to get a better approximation to the exact strain energy, right? So what you will see is that, at least in the project, the first three meshes that you solve are already enough to approximate the exact strain energy within a 1% of its value. Yeah? Again, also depending on the type of problem. For smooth problems, it's different than for non-smooth problems, but we will look at all of these things. Yeah?
Why are we calculating the error with the space norm and not like the absolute value or with the Euclidean norm?
Yeah, that's a good question. Why we're computing the error in the energy space and not another form of error? Well, as it turns out that there are different ways to compute errors, right? We like computing errors in the energy norm because we're looking at bilinear forms and we're looking at derivatives. And of course, in the sense of finite element solutions, we know that the displacements are more accurate than the strains or the stresses, right? Than the derivatives of the field. So in a way, computing errors with respect to high order derivatives is going to be more strict than when you compute the error, for instance, with respect to the exact displacement field. So what you're talking about there is we have an error in L2 norm, right? Where we just take not the derivatives, but we can do the integral and then look at the field and subtract the exact solution, right? That is the so-called L2 error. And so, again, that is going to converge at a faster rate than an error measure that takes into account the derivatives, all right? Okay, let's stop here. And we will continue in the next lecture with finite element discrete equations.